In this lecture, we will derive boundary conditions for steady current densities. So we have seen in one of our previous lectures when we derived the equation of continuity from the principle of conservation of charge that del dot J is equal to minus dou by dou T of the charge density. Now, I've already told that for steady current densities, this term is equal to 0. So it implies del dot J is equal to 0 for steady current densities, or its integral form is J dot ds over the surface, closed surface S is equal to 0. Now, we also know that del cross E for electrostatics is equal to 0, and this E is simply given by J over sigma, that is J is equal to sigma E, the point form of the Ohm's law. So putting this, I will have del cross J by sigma is equal to 0, or in integral form I can write it as over a closed circulation C or curve C, J by sigma dot dl is equal to 0. Now we have these two integral equations. Now from these two we can find the boundary conditions. So from J dot ds over a closed surface S is equal to 0 by making a Gaussian surface or pillbox. Let us say this is medium 1, this is medium 2, and this is A and 2, and this is A and 1. So I will make a pillbox, and I will assume that this pillbox is going to have this height delta h, which will tend to 0 in the limiting case, and this surface area is delta s, and this is also delta s. So J1 dot A and 2 for the top surface plus J2 for the bottom surface dot A and 1 plus J and the curved surface is equal to 0 from this equation. Now this will tend to 0 when delta H tends to 0, because the surface area is going to be 0, this curved surface area. Now I know that A and 2 is equal to minus of A and 1. So I can write it as now J1 minus J2 dot A and 2 is equal to 0, or J1n is equal to J2n. Now for this derivation, I have assumed that this equation is valid on the boundary also. And of course, it has been derived from Maxwell equations, and those are valid on the boundaries also. So it is a given now that we can derive the boundary condition like this. Now, let us take another equation. J by sigma dot dl over the closed curve C is equal to 0. Again, this is medium 1, this is medium 2. I will take the circulation along this curve, delta L, delta H, in the limiting case when this delta H tends to 0. So similarly, I can find and I can write J1 over sigma 1, the tangential component or the component along this delta L, minus J2 tangential over sigma 2 is equal to 0, or J1t over J2t is equal to sigma 1 by sigma 2. So these are the two boundary conditions for steady current densities. First one is that the normal component for steady current density is continuous, and the tangential component is having a discontinuity whenever there is a change in the conductivity of the media, and this is given by this equation. These are the two now boundary conditions which we may use for solving various numerical problems. Now we will try to find what happens in a case when the medium is homogeneous. So we have seen that del cross J by sigma is equal to 0. Now I can take this sigma out of this del operator if and only if this medium is homogeneous, that is, this sigma is independent of space coordinates. So assuming that the media is homogeneous, then I can write del cross j is equal to 0, or del cross j is equal to 0. Now it is similar to that electrostatic field, that its curl is 0. So now it implies that j can be written as a gradient of some scalar quantity, and del square psi is equal to 0 will be the corresponding Laplace equation in psi, and this is a scalar potential field. So any problem in steady current for homogeneous medium can be solved similar to an electrostatic problem if we have appropriate boundary conditions, and we can find this steady current density from the gradient of this scalar potential field, similar to any electrostatic problem. That's why this is one of the reasons which I have told in the beginning of steady current chapter, that electrolytic tanks were used to find solution to some electrostatic problems which were not solvable directly using analytical methods. And that's why electrolytic tanks were used to map the potential distribution for the difficult to solve electrostatic boundary value problems. Now, what will happen when there is a steady current which flows across the boundary between two media having different conductivities? We will find that there will be a buildup of surface charge, so that these boundary conditions are met or followed. So let us say that these are two media, 1 and 2. This is conductivity sigma 1, this is conductivity sigma 2, and its permittivity is epsilon 1, its permittivity is epsilon 2. So from our condition that J1n is equal to J2n, I can simply write it implies sigma 1 E1n is equal to sigma 2 E2n. Now we also know that D1n minus D2n is going to give us the surface charge density, or it implies epsilon 1 E1n minus epsilon 2 E2n is going to give the surface charge density. Now I can put the value of E1n or E2n. Let us say I can write E2n is equal to sigma 1 by sigma 2 E1n. So I will put this value here. So epsilon 1 E1n minus epsilon 2 sigma 1 by sigma 2 E1n is equal to rho s, or I can write E1n common epsilon 1 by epsilon 2, or let us not take common the epsilon, minus sigma 1 epsilon 2 over sigma 2 is equal to rho s. Now when this surface charge can be 0, this will be 0 if and only if epsilon 1 minus sigma 1 by sigma 2 epsilon 2 is equal to 0, or epsilon 1 by sigma 1 is equal to epsilon 2 sigma 2, or the relaxation time constant of the medium 1 is equal to the relaxation time constant of the medium 2. So there will not be a buildup of any surface charge density on the interface if and only if the relaxation time of both media are equal. But this is a very ideal case, and usually it cannot be possible that these relaxation times are equal. So you will find that whenever there is a steady current density in a media or various medium, 1, 2 or various media, then on the interfaces there will always be a buildup of surface charge density because of this conduction current, so that this charge buildup now creates a field, and it helps in the satisfying of various boundary conditions, and those boundary conditions are J1t by sigma 1 is equal to J2t by sigma 2, and J1n is equal to J2n, and D1n minus D2n is equal to rho s. So you see that in this way we can find the surface charge density on the interface between two conducting media of different relaxation time constants. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join our Telegram group, whose link is given in the description of this video. Thank you.